Hey guys, so today I want to talk about the gas laws. Now, this is three laws which describe the way that pressure and volume and temperature interact with each other, but more than just like how they affect each other, but it's also like mathematically how do they affect each other. Like if the pressure changes, how could you calculate how the volume changes, that sort of thing. So the first one I want to look at is Boyle's law. So Boyle's law is all about pressure and volume. How are pressure and volume related? Here's a little demonstration showing you what goes on with pressure and volume and how they affect each other.
Okay, now let's see what happens if we put a balloon in the vacuum chamber. All right, balloon in a vacuum chamber. 3, 2, 1. Oh, it's already getting bigger. See if we can get it the full size of our chamber. Look how big it's getting. It's gonna fill up our whole chamber. Might pop. Whoa. Whoa. Square balloon. That's so cool. I just made a square balloon, everybody. Look at that from different sides. Okay, let's turn off our vacuum pump. See if we can get our balloon. So I'm gonna open up the valve, let in more air pressure. It should squish back down. Wow, that was cool. It filled up the whole chamber.
Okay, so this is Boyle's law. Okay, at constant temperature, we're not going to change the temperature here. The volume of a gas is inversely proportional to the pressure. Inversely proportional means it's opposite. So if I decrease that volume, make it smaller, it's going to increase the pressure. Okay, there's going to be more collisions in there. If I increase the volume, make it bigger, there's going to be more empty space, and so the pressure is going to decrease. They're opposite each other, inversely proportional. Right? Increased volume, decreased pressure. Decreased volume, increased pressure. So here's kind of a particle diagram of this. If I have two syringes, in which case they can change size, I start with one where the volume is 100 milliliters, and I basically compress it down to 50 milliliters. Right? That volume is decreasing. What's going to happen to the pressure? It's going to increase. Okay, that pressure is going to increase because now that there's less empty space there, those particles, even though they're not moving any faster, they're going to hit each other more because there's just less empty space for them to move. Okay, now remember, this is all about the temperature not changing. It's just the volume changes, so now they're closer together and they're going to bump into each other more. Now, mathematically, expressing Boyle's law, you can express it with this equation. Okay, P1 times V1 equals P2 times V2. The P stands for pressure, the V stands for volume. The 1 and the 2 stand for this is what the pressure and the volume were at the beginning, and then this is what the pressure and volume were after. So kind of coming back here, this would be P1 over on the left here. We would have P1 and V1, whatever pressure this is and whatever volume this is, and then this would be P2 and V2, whatever pressure this is, and volume would be 50 milliliters. Okay, V1 would be 100 milliliters. Right? So that's the mathematical form here. Here's how it works. Let me show you an example problem. Okay, so Boyle's law problem here. A weather balloon with a volume of 1,700 liters. It's at a pressure of 96.3 kilopascals. It rises to an altitude of 1,000 meters. That 1,000 doesn't actually matter. It's just telling you how high it goes. What you want to pay attention to is the volume and the pressure. Okay? This is where the atmospheric pressure is measured to be 60.8 kilopascals. All right, so the pressure is decreasing up there. It's a smaller pressure. Assuming there's no change to the temperature or the amount of gas in the balloon, calculate the weather balloon's final volume. So since the pressure is decreasing, Boyle's law says that they're inversely proportional. This volume should increase. Okay? So just to kind of illustrate so we know where we're going, the pressure here is decreasing, so the volume should increase. Now, I'm going to kind of underline the important piece of information. This right here is V1. This right here is P1. Okay, it doesn't really matter, it's going up to 1,000. This right here is P2. And then it's asking us for the final volume, which is V2. Okay, so my equation, go ahead and write it here. We have P1 times V1 equals P2 times V2. I'm going to take everything that's up here, I'm just going to plug it into the equation. Okay, so P1, right there, is 96.3 kilopascals times V1, 1,700 liters, equals P2, right there, 60.8 kilopascals, times V2. That's the only thing I don't know. I'm just going to make that my variable x. Okay? Find x. All right, well, to do that, I'm first going to simplify this side. So 96.3 times 1,700. Calculator says 163,710, and this is kilopascals times liters now. Okay, just to get the units there. This is still the same number, 60.8 kilopascals times x. So all I did is simplify this right here. Next, I need to get x by itself. To do that, I need to divide by 60.8. I need to divide by this. So it cancels it, and the only thing that's going to be left on this side is x. So over on this side, I'm dividing by 60.8 kilopascals. Okay, so divide by the same thing on both sides. This cancels kilopascals but leaves liters. All right, it leaves the liters. So I'm going to take the 163,710 divided by 60.8, and I get that number, 2,692.598684 liters. Looking at my original numbers here, we had 3 sig figs, 2 sig figs, and 3 sig figs. So 2 is what I rounded to. So I'm going to round that to 2,700. 2,700 liters is what the new volume would be, which is greater. Okay, your turn. So I want you to try this problem, pause the video, and give it a try. I'm going to read it here. Atmospheric pressure on the peak of Kilimanjaro can be as low as 0.20 atmospheres. If the volume of an oxygen tank is 10 liters, 10.0, at what pressure must the tank be filled so the gas inside would occupy a volume of 120 liters when you use it on the peak at that low pressure? So this can be a little confusing because this is your P2. The first number it gives you is actually P2, so be careful of that. And then this is your V2. This is your V1, what you started with at the bottom of the mountain. So you have this volume, and you go to the top of a mountain and you want it to be this volume at this pressure. Okay? So the question is what will the pressure be to start off with in the tank since it's only 10.0 liters? Go ahead and pause the video and see if you can figure that out. Okay, so my equation, P1 times V1 equals P2 times V2. Take these numbers and plug them in. So we have P1, don't know, that's what I want to figure out, times V1, which is 10 liters, equals P2, which is 0.20 atmospheres, times V2, which is 120 liters. Okay, first thing I'm going to do is I'm going to simplify this. So that is 0.2 times 120, which is 24 atmospheres times liters. Okay, and And then on this side, I didn't do anything, so it's still x times 10.0 liters. Now I want to get x by itself, so I'm going to divide both sides by 10.0 liters. Liters cancels, so 24 divided by 10.0 gives me 2.4 atmospheres. And this, my x, so that is P1, the pressure I would want to start with in the oxygen tank at 10 liters. Okay, a higher pressure so that when we get up there and we release it from the tank to make it larger, at that low pressure, it would be how much oxygen we actually need. Okay? Okay, so this next law is called Gay-Lussac's law. It was named after a guy with the last name Gay-Lussac. The first one was named after a guy with the last name Boyle. It was Robert Boyle. He's the guy who kind of did the original discovery. Gay-Lussac was working more with temperature and pressure. So Gay-Lussac's law is all about how temperature and pressure and temperature, how they're related. So here's a demonstration of Gay-Lussac's law.
Deep in Buster's basement, changes are occurring in his water heater. Changes that could affect his life. Oh, look, we've turned red.
175 PSI.
The suspense is killing me.
Now it's really starting to accelerate.
All that potential just waiting.
325.
Oh, God, it's any second now. I don't want to turn back and look at the pressure anymore. I don't want to take my eyes off of it.
330.
Okay, I'm going to do some live math here. The hot water heater itself is 18 inches in diameter. Now, for the area of that, it's pi r squared, which equals 254 square inches of the bottom. Now, you've got a pounds per square inch pressure inside of 336. Multiply that by 254, you get 85,500 pounds of pressure. Let me say that again, 85,500 pounds of pressure pushing against the bottom of the heater. You would fail too.
335.
You know what I see? I see a hole in the roof, man!
Holy cow. Now that's what I call mission accomplished.
I wish you could be here for this kind of explosion. Because when the hot water heater finally blows, we're staring right at it because we know where the zone is. And the thud that comes out of it is so deeply guttural and still whoa kind of thud. It's great. Watch it again.
Okay, so this is Gay-Lussac's law. The pressure of a gas is directly proportional, not inversely, directly proportional to its temperature if you don't change the volume. Okay, so we're not changing the volume in this case, it's just pressure and temperature, but they're directly proportional. So this means that if you increase the temperature, you're also going to increase the pressure. They're going to both increase together. If you decrease that temperature, you're also going to decrease that pressure. Okay, so increase the temperature, pressure goes up. Decrease the temperature, pressure goes down. Okay, now I did mention that this is at a Kelvin temperature. When we actually do some math here, it's much better to deal with it as Kelvin, the absolute scale, where 0 Kelvin would be absolute 0, and every temperature then is an increase from absolutely no temperature at all, absolutely no kinetic energy at all. Okay, so we're going to focus on this law. We're definitely going to do Kelvin. All right, so here's a little diagram of what's going on. We have two containers here. The volume is not changing. All right, there's a steel container, and so it's not going to blow up. The volume's not going to change. They both contain the same amount of air. All right, the first one is at 300 Kelvin. That's about room temperature in Kelvin scale. So particles are moving around. If we were to heat it up, get those particles moving faster, heat it up to 600 Kelvin, what would happen to the pressure as that temperature increases? Well, if the temperature increases, that means the pressure is also going to increase because they're directly proportional. Okay? If they're moving faster, they're going to bump into those container walls a lot more often, and they're going to bump into them harder, so that pressure is going to increase. That's Gay-Lussac's law. Now, mathematically, the formula is this. P1 divided by T1 equals P2 divided by T2. Okay, so this one's slightly different from the last one. They're dividing instead of multiplying. Again, 1 and 2 stand for what you start with versus what you end with. P is pressure, T is temperature. Now, the temperature has to be in Kelvin. It has to be. So how do you convert to Kelvin? So Kelvin scale, otherwise known as the absolute scale. Okay, first off, you have the temperature in Celsius. Normally, this is where water freezes. That's what the Celsius scale is based off of. So water freezes at 0, and then it boils at 100. So the Celsius scale is based off of this. Now, absolute 0 would be negative 273 in the Celsius scale. The Kelvin scale is the exact same thing as the Celsius scale, except it shifts the whole scale down so that 0 is absolute 0. Okay, which means that the point where water freezes, which is 0 degrees Celsius, would be 273 degrees above absolute 0, so that would be 273. And then the point at which water boils, 100 degrees Celsius, would be 373 degrees above absolute 0. So for all of these, all you have to do to go from the Celsius scale to the Kelvin scale, all you have to do is add 273 to it. Now, if you want to go backwards, okay, you have Kelvin and you want to go back to Celsius, then you subtract 273. So they're just basically offset by 273. Okay, so let's try converting to the Kelvin scale, or converting from Kelvin to Celsius, Celsius to Kelvin. So start with, we got Celsius, and we're going to convert to Kelvin. So what to do there, all you have to do is take the Celsius and add 273. So 0 degrees Celsius, add 273, that equals 273 degrees Kelvin. Okay? 100 degrees Celsius, add 273. That equals 373 degrees Kelvin. Okay? 25 degrees Celsius, add 273. Okay? That equals 298 Kelvin. Negative 12 degrees Celsius. Go ahead and do this one. Careful, it's a negative number. Add 273 to it, and we get 261 Kelvin. Okay? These are always going to be positive, by the way. Kelvin is always positive. Now, to go backwards, let's say it's 270 Kelvin. What we're going to do is we are going to subtract 273. Okay, so going backwards, subtract 273, the exact opposite. So 270 minus 273 gives me negative 3 degrees Celsius. Right? That one's a below 0 for Celsius, but 273 above absolute 0. So 235 minus 273 is 35, negative 38 degrees Celsius. Okay, go ahead and try this last one here. 734 degrees Kelvin. So if we subtract 273, we would get 461. So now let's actually try Gay-Lussac's law. Okay, so Gay-Lussac's law, P1 divided by T1 equals P2 divided by T2. All right, so this problem here, what is the pressure of a fixed volume? That means we don't have to worry about it. This is Gay-Lussac's law. It's at 30 degrees Celsius if it has a pressure of 1.11 atmospheres at 15.0 degrees Celsius. Okay, so this right here, this one is P1, this one is T1, and then this would be T2. Okay, so what we're looking for is P2. We're looking for P2 in this case. Now, we cannot do this with it in Celsius, so we have to convert both of these into Kelvin. So I'm going to add 273 to this, so that would be 288 Kelvin. I'm going to add 273 to this, so that would be 303 Kelvin. Okay? Now, when I add them, each of these has a decimal point, but this one does not. Okay, so I'm rounding it so it doesn't have a decimal here. All right. Now that we have them in Kelvin, I can go ahead and take these numbers and plug them into the equation. So I've got P1. P1 is 1.11 atmospheres divided by T1, which is 288 Kelvin, equals P2, I don't know what that is, so I'm going to put X, divided by T2, 303 Kelvin. Okay, make sure that these are in Kelvin, the temperatures. That's the most common mistake people have. Okay, so first thing I'm going to do is I'm going to simplify this side. So we've got 1.11 divided by 288. This gives me 0.0038541667 ATM divided by Kelvin still. Okay, this hasn't changed. So 303 Kelvin still. Now I want to get X by itself. To do that, because this is on the bottom, I need to multiply by 303 Kelvin on both sides. Multiply by 303. That will cancel it over here, leave nothing but what I'm looking for. So this times 303 equals 1.1678125, and then the kelvins also cancel, so we're left with just atmospheres. Okay, that's my final answer. So this had 3 sig figs, 3 sig figs, 3 sig figs, so go ahead and round that to 1.17 atmospheres. And there is my P2, the answer. Your turn. Pause the video and give this one a try. We have the pressure of a gas in a sealed container. It's 350.0 kilopascals at room temperature of 15 degrees Celsius. Canister is placed in a refrigerator. Okay, so the volume is not going to change. It drops to the temperature by 20 degrees. It's down to -5 degrees Celsius. So what is the new pressure in that canister if it's cooling down to -5? Got an answer? Okay, so first off, this right here is P1. This one is T1. And then this one is T2. It's cooling down. So what we're looking for is the new pressure, P2. So P1, T1 equals P2 over T2. First thing, let's convert these to Kelvin. Okay, so add 273 here, and that gets me 288 Kelvin. Add 273 here, gets me 268 Kelvin. Okay, so T1 is 288 and T2 is 268. So I'm going to take these numbers all and plug them in here. P1 is 350.0 kilopascals divided by T1, which is 288 Kelvin, equals P2, that's the one I'm looking for, divided by T2, 268 Kelvin. Rearrange all this. X equals 325.69444444. Round that to, it says 4, 3, and 3 sig figs. Okay, so that would be 326 kilopascals. Okay, so the last law, Charles' law, named after a guy with the last name Charles, okay, asks how volume and temperature are related. The relationship between volume and temperature. So here's a demonstration of that. So Charles' law is that the volume of a gas is directly proportional to its temperature, again in Kelvin, as long as you're not changing the pressure. Like, but this experiment was done at normal atmospheric pressure the whole time. Okay, so the volume is directly proportional to its temperature. This means that if the volume is increased, the temperature is going to increase. Or if you heat it up, increase that temperature, then it's going to get bigger. It's going to get a bigger volume. If you decrease that temperature, make it colder, then the volume is also going to decrease, okay, at constant pressure. So what's going on with the particles here? I got two diagrams here. So in both these, same amount of gas. Okay, now this one, the volume can change. It can go up and down. There's normal atmospheric pressure around it, pushing on it. So if the pressure in there were to change, it would just adjust the volume until the pressure was, again, the same. It's basically able to adjust so it's always at the same pressure. Okay. Now, what's happening here is we have a small volume with very slow molecules. These are once again at 300 Kelvin, about room temperature. Okay. And it is being heated up to 600 Kelvin. So the temperature is increasing. What is going to happen to the volume? Volume is going to increase as well. Okay. So the volume is going to increase. It's going to get bigger. You can see it's a larger container. And the reason why this is because they push on that lid, but instead of increasing the pressure, it just moves the lid. If the lid doesn't move, the pressure goes up. But since the lid moves, it just pushes that lid out of the way, and you get a bigger volume. All right, same pressure. So this is Charles' law. Okay. Now mathematically, Charles' law is similar to Gay-Lussac's law, where it is something divided by the other thing. It's volume 1 divided by volume, or temperature 1, is equal to volume 2 divided by temperature 2. Okay, so we're dividing them again, 1 and 2, beginning and ending again. Again, though, all temperatures, for all of the laws that you deal with gas laws, they always have to be in Kelvin. So anytime you're dealing with a temperature, make sure it's in Kelvin. You add 273 to whatever it is in Celsius. So here's an example problem. Okay, so here's Charles' law. Charles' law, we have a gas with a volume of 2.0 liters and sets a temperature of 20 degrees Celsius. What is the volume of the gas if the temperature is increased to 25.0 degrees Celsius? So the temperature is increasing by 5 degrees, volume is going to change. All right, should increase. So we have V1 divided by T1 equals V2 divided by T2. But first, we got to convert these temperatures into Kelvin. So 20 plus 273 equals 293 Kelvin. 25 plus 273 equals 298 Kelvin, 5 degrees greater. Okay, so then I go ahead and take these numbers and plug them all in. This is my, let me grab the other color. This is my V1. This would be my T1. This would be my T2. And I am looking for the new volume, so I want to know V2. All right? So plug all these numbers in. V1 is 2.00 liters. T1 is 293 Kelvin. Equals V2, don't know it, X, divided by T2, 298 Kelvin. Okay, so I'm first going to simplify this. So 2.00 divided by 293 is 0.068259386 liters divided by Kelvin. Still equal to the same thing, 298 Kelvin on bottom there, X over 298. Now to get X by itself, times 298 Kelvin on both sides. Gets rid of it over here, so it's just X. Okay. This side is 298 times what we had before, which is 2.034129693, and Kelvin cancels, so we're left with liters. Now, rounding it, each of these had 3, so I'm going to round this to 3, 2.03 liters. So the volume did increase a little because of that increase in temperature, but it's only 5 degrees, so it didn't increase by a lot. 2.00 to 2.03. Okay, your turn. So we have a beach ball. It's inflated to a volume of 25 liters, and it's at 15 degrees Celsius. Okay. During the afternoon, that volume then increases by a liter up to 26 liters. So the beach ball gets a little bit bigger. What is the new temperature then, since it increased? Pause the video and give us a try. Okay, got an answer? So first off, I am going to change this to Kelvin.